Okay, so what we are looking at today is the derivative as a function. So we looked at the derivative at a particular value. So we're giving you values to find the derivative at, but we can actually do something bigger. So here we took the function f of x equals x squared. Find the derivative of f at x equals 4. So we use our limit definition where the a number is 4. Figured out f of 4 plus h. F of 4 is 16. We plug those things in. The 16s cancel. Everything else has an h in it. And we get 8 plus h. We do the limit as h goes to 0. And we end up with 8. So the derivative of f of x equals x squared at x equals 4 is 8. So the slope of the tangent line at x equals 4 is 8. But now the question is, could we do that in general? So instead of just calculating the derivative at x equals 4, what if I wanted to calculate the derivative for like 5 different numbers? It'd be a pain in the butt to do that same work for 5 different numbers, especially when I could just do the work in general once and get a formula for the derivative, and then I could plug in whatever numbers I wanted. So we're going to use our definition of derivative. But we're not going to plug in a number for x. We're just going to leave it as x. So this means we're doing more algebra work. And this is actually similar to the way the question was asked in pre-cal. So we're going to figure out f of x plus h. And we're going to figure out f of x. And we're going to write those in. And then it'll be all over h. So the limit as h approaches 0. Then f of x plus h. That is, our function is do the thing squared. So our thing is x plus h squared. And then we're going to minus f of x. F of x in this case is just x squared. Now, x plus h squared, I can FOIL that out. X plus h times x plus h. So down here, I'm going to have still the limit. But now that'll be x squared plus 2xh plus h squared. Then we have minus the x squared all over h. And here we can see those x squared terms cancel out. Everything that's left over has an h, so I'm going to factor it out. So we have h times 2x plus h, all divided by h. The h that's factored out, so it's h times this thing divided by h, those can cancel. But just make sure when you factor out that h, that what you wrote inside is the result you would get from pulling it out. So you can remultiply. H times 2x would get you back to 2xh. H times h would get you back to h squared. So they are an equivalent statement. So now I can plug in the limit as h goes to 0. Now I can substitute in the 0. So I have 2x plus 0, which means my derivative is just 2x. So for f of x equals x squared, f prime of x equals 2x. So we just proved that conclusively. So if I want to know the derivative for any x value of the function x squared, I just plug that x value into the formula 2x. So questions on how figuring out the derivative in general works there. So we have some fancy definitions. So this is the definition of the derivative, but they wrote x instead of the a. So a function is said to be differentiable at a if f prime of a exists, which means that limit there exists for the x value a. Then we can expand that and say, well, what about if that's true for a whole bunch of a values? So we say a function is said to be differentiable on some set S if it's differentiable at every point in an open set S. And a differentiable function is one in which f prime of x exists on its domain. So most functions we've studied so far are differentiable everywhere. So we can figure out the derivative, and then that formula is the derivative for that function. So today, though, we're just going to focus on what this derivative idea means. What kind of information can we extract from it? What can we use the derivative for? So there's a lot of different ways of writing derivative. We've got them over here on the side. So there's dy dx, or sometimes we'll write y prime. Sometimes we'll write f prime of x. And sometimes if we're feeling really annoying, we'll write d dx of f of x. So the derivative is a process. It is a thing we can do to both sides of an equation. So just like I can square both sides of an equation or square root both sides of an equation, there's some caveats for using the square root. There's some caveats at times for using the derivative, but we can apply it as a thing to be done to an equation. So what we're going to learn is, when would I choose to do that? What is that going to tell me? All right, so this one is saying determine the value or values of x for which the tangent line to f has slope equal to -1/72. So they gave us this ugly function, f of x equals 6 over the square root of x. And they are saying, find the derivative and then set that derivative equal to -1/72. So this graph does some sort of crazy shape, and we want to figure out where is the slope going to be. That particular -1/72 is almost a flat line, but slightly downward tilting. So there's our formal definition of the derivative. And now we're going to start using our function notation. All right, so my first one, f of x plus h, I look at my f formula. And my f formula says, For f of a thing, do 6 divided by the square root of the thing. So in my formula, it's going to be 6 divided by the square root of, and then the thing here is x plus h. Minus, now we're just going to do the function itself, which is just 6 over the square root of x. And then that is all being divided by h. So the first change I'm going to make is instead of fractions all divided by h, I'm going to move this h up to the side. So it's 1 over h times, and now I'm just going to have those fractions. Now we got to kind of consider, what are we going to do with these fractions? So some way I'm supposed to be able to combine stuff, do some math magic on top, and eventually I will have an h that I can cancel. So first thing is, those are two separate fractions. So we're going to combine the fractions by getting a common denominator. So this 6 over the square root of x plus h needs to get multiplied by square root of x over square root of x. This 6 over the square root of x needs to get multiplied by the square root of x plus h over the square root of x plus h. So the bottom of that fraction is now square root of x times square root of x plus h. Now, combining the tops of the fractions, we have to be careful because there's subtraction between them. The top of the first fraction would be 6 square roots of x. The top of the second fraction would be 6 times this other square root. So that's one thing. So I'm just going to write it as minus 6 times the x plus h square root. Still no way to cancel my h. But I put the fractions together at least. Now on top, I've got two things being subtracted with a square root in there. So I'm going to multiply by the conjugate. So it's going to look pretty gnarly. So our conjugate is 6 square root of x and then plus 6 square root of x plus h. And then I'm going to write that on the bottom as well. 6 square roots of x plus 6 square root of x plus h. All right, on the top, we're going to FOIL that, distribute it through. On the bottom, we're just going to leave it all multiplied. We're not going to actually distribute through. Because the top is where I want that h to show up so it'll cancel. So we still haven't substituted in the 0 for h, so we still have the limit. We still have the 1 over h out front. On top, when I do the FOIL distribution, I'm going to get the first times the first and the last times the last because we have a conjugate, so the outer and inner part of the product are going to cancel out. So 6 times 6 is 36. Square root of x times square root of x. I'm going to write square root of x squared. Then we'll have minus 6 times 6 is also 36 times square root of x plus h squared. So on top, that becomes 36x minus 36 times x plus h in parentheses. All over, same annoying denominator. Now this negative 36, I'm going to distribute through. And that not distributing that negative sign appropriately here, it'll look like you did things right, but your answer will be just slightly off. So we'll have 36x minus 36x minus 36h. All right, 36x minus 36x cancel. Now the top is just minus 36h. Now I can finally cancel the damn h's. Once we have canceled the h, the 1 over h, now we plug in 0 for h. So the top is just negative 36. The bottom will be the square root of x times the square root of x plus 0, which will just be the square root of x, and then times 6 square roots of x plus 6 square roots of x plus 0. So square root of x times square root of x is actually square root of x squared, which is just x. And then inside 6 square root of x plus 6 square roots of x is 12 square roots of x. And the 36 and the 12 can actually reduce. So we have negative 3 over x square roots of x. So all of that to find the derivative formula. We haven't answered the question. We just did the first step. The question was, at what x values is the slope of the tangent line equal to negative 1 over 72? So now we are supposed to solve f prime of x equals negative 1 over 72. So down here, this formula I got, this is f prime of x. So I'm going to write it in place of f prime of x. So this is now negative 3 over x times, now instead of square root of x, I'm going to change this to x to the 1/2. So our x times x to the 1/2. So I know my x has an invisible 1 as a power. So what happens to these x's here? X to the 1 times x to the 1/2. What can I do with the powers? These are close enough to add, not close enough to multiply. So we have negative 3 over x to the 3/2 equals -1/72. All right, now I'm going to cross multiply. Ugh. What is 3 times 72? 216, yeah. So I have -216 equals -1x to the 3 halves. Divide by the -1. So now I have positive 216 equals x to the 3 halves. So how do I get rid of the 3 halves power? So part of what we want to think about, what do we do with that 2/3 though? I just multiply by it? Yep, we're going to use it as an exponent. So we're going to raise both sides to the 2/3 power. So don't do 216 squared first, do the cube root of 216 first. 216 is 6 cubed. So that's the cube root part, the 1/3 part of the power. And then we have 6 squared, which is 36. But this is also 216 raised to the, put 2/3 in parentheses, enter, calculator spits out 36. I was just talking y'all through what's happening number crunching wise. If you were curious, you don't have to do it by hand. Calculator is a perfectly reasonable tool, and this is its purpose. So it turns out that at an x value of 36, the function 6 over the square root of x has a tangent line slope of -1/72.
I just used the exponent part. I left the x into square root of x. And so I got x into square root of x equals 216, taking that equal plus one reason.
So can we put a negative number inside the square root of x? But if it was a slightly different problem, like sometimes we will have that plus or minus. All right, now this one is an oh dear God, I want to kill myself. I mean, we even get a meme that's like, oh my God, why? But the question it is asking here is actually an extremely common question. Hold on. I got to scroll a bit so I can make more room, because we all know I write too big. And this is going to be a lot of big writing. So this is saying determine the values of x for which the tangent to f is horizontal. So a horizontal line, a flat line, has a slope. So a perfectly flat line, does it have a rise? Does it ever go up or down? Nope, all it does is go over, over, over. So the slope of a horizontal line is 0. Now think about a graph. Like if I'm thinking about kind of the way a parabola works, like an upside down parabola. So kind of like the hill on a roller coaster, I go up, 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 up. It starts to like slow a little, and then at the top of the hill, my tangent line would rest perfectly flat. And then I would start going down. So when the tangent line is flat, when the derivative is equal to 0, that is where we have a like tipping point for our slope of the tangent line. That tipping point, though, is either the top of a hill, or if we were looking at a normal parabola, like we're swooping down, and then it'll bottom out before we start swooping back up again. So we very often in calculus, it's like, I don't know what to do. Take the derivative and set it equal to 0. Like about 70% of the time, that's probably what the problem wanted you to do. So here we are doing our first example of what we're going to do most in this class. It's just the function is, even if you know the shortcut rules, this function is gross. Without the shortcut rules, it's like, but we're going to do it. So we're doing ugly derivatives today. So next week we can start learning shortcut rules. We're not going to ask you to do ugly long derivatives on the exam. We made you do that on the last exam, not this one. My hope is to have the exam graded by next Tuesday. Okay. All right, so the limit as h goes to 0. So when I look at my function f of thing, I have thing squared divided by thing plus 10. The thing I'm putting in for this first one is x plus h. Now I'm already going to take my all divided by h and just write that as 1 over h. Especially whenever we have fractions, that's just like habitual, like, let me just put this in front. So my function formula is thing squared over thing plus 10. My thing here is x plus h. Minus, and then I'm just going to write the function formula. Let's be careful. So that's substituting for the f of x plus h minus, I'm going to substitute for f of x now, x squared over x plus 10. So in order to get these together, we're supposed to get a common denominator between those two fractions. And the common denominator is those two denominators multiplied. So I get the limit as h goes to 0 still, and our 1 over h. We're questioning our life choices. So the x plus h squared, x squared plus 2xh plus h squared over x plus h plus 10. So in order to combine these fractions, this fraction is going to need to be multiplied by x plus 10 over x plus 10. Minus, then my other fraction was x squared over x plus 10. To get a common denominator, this one is going to get multiplied by x plus h plus 10 over x plus h plus 10. All right, so let's put some parentheses back in here, just so we're doing safe math. Ugh. Still with the limit as h goes to 0 of 1 over h times, I hate my life. All right, so we're going to run the x through all of these terms. So x cubed plus 2x squared h plus xh squared. Then we're going to run the 10 through all of those. Plus 10x squared plus 20xh plus 10h squared. All over x plus h plus 10 times x plus 10. Minus. Now this other one isn't as bad. We're just having to multiply x squared through. But then we've got that same denominator on the bottom, the x plus h plus 10 over x plus 10. So on top, we'll have an x cubed plus x squared h plus 10x squared. Now notice the subtraction is still between these two fractions. This subtraction, though, is going to need to be distributed through everything on the right fraction. So when we combine these fractions together, that subtraction in between has to apply to everything in that second fraction. All right, so on top, x cubed plus 2x squared h plus x h squared plus 10x squareds plus 20xh plus 10h squared plus, I really need to remember to write smaller. Now it'll be minus x cubed minus x squared h and minus 10x squared. So our negative x cubed is going to cancel the positive x cubed. Minus x squared h. It's like terms, but it doesn't cancel anything out. But that minus 10x squared does cancel the positive 10x squared. So every term that didn't have an h got canceled. All right, so now we're going to write our leftovers. So the minus x squared h with the 2x squared h. So 2x squared h's minus an x squared h is going to leave me with a single x squared h plus xh squared plus 20xh plus 10h squared. Everything on top has an h. I'm going to be a little lazy because we've written so damn much. So that h cancels That one's going to become an h to the first. That h cancels. That's going to become an h to the first. Now that I've canceled the h, now I can substitute in the limit as h approaches 0. So that will be x squared plus x times 0 plus 20x plus 10 times 0 all over x plus 0 plus 10 times x plus 10. So we have x squared plus 20x over x plus 10 squared. So we did all that work to find the formula for the derivative. The question, though, was when is the tangent line horizontal? When is the slope of the tangent line equal to 0? So the question was actually asking us to solve f prime of x equals 0. So I'm going to take that formula and put it in here. X squared plus 20x over x plus 10 squared. So in order to solve this equation, like it's a fraction right now, I want to clear the fraction, which actually means that annoying denominator is just going to completely disappear. Now, whenever we multiply by something with a variable, we do kind of have a caveat to the side, like x plus 10 is not allowed to be 0. But if we look back at the original function was dividing by x plus 10. So the original function is already not defined there. So, like, that's a caveat we have, but we already had it. So, as long as we don't get a 10, or I'm sorry, negative 10. As long as we don't get a negative 10 when we're solving the rest of this, we're fine. So x squared plus 20x is equal to 0. So what is x going to equal? How'd you get 0 and negative 20? Yep. So x squared plus 20x has an x in common. And now that it's in a factored form, our zero factor property of two things being multiplied are equal to 0, then one or the other of the things is 0. So the first thing is just x, so x could be 0. The second thing is x plus 20, which we minus the 20 over, and we have x equals negative 20. So those are the two values on this particular crazy function when the derivative is equal to 0, when the slope of the tangent line is 0. here is the graph of that equation. X squared all divided by x plus 10. We can see at 0, it looks like it's flattening it out. And then down here at 20, that looks like the peak of that weird kind of sideways curve. So this is actually a tilted hyperbola. But those 2 points are where the slope of the tangent line would flatten out. So we did a whole lot of crazy work, but we can actually see the numbers we solved for in the picture. So now we're going to talk a little more big picture. What do these things mean? So looking at the graph of our function here, we're going to talk about these words. When is the function decreasing? When is the function increasing? So what do those words mean?
Would it be like the tipping point, basically, from where it stops? If we are past that point where it's 0?
So the 0 points are where it's neither increasing nor decreasing. So when we get a 0 point, that's when it's changing from one or the other. So like I see I've got a tipping point around here and around here. Not that they gave us good X values. But so that's when the graph is changing. So when it flattens out, it's neither increasing nor decreasing. But when we say a function is increasing, like what does increasing sound like something's doing? So that's jumping to the end, yes. So increasing means things are getting bigger, right? They're going up. When we talk about a graph going up, I think of it like a roller coaster track. So if I'm riding along the track and I'm going up, 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 up. Oh, it's starting to slow down, but I'm still going up. So that going up part is increasing. Then after our tipping point, oh, now we're going down, 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 whoosh. And then at the bottom of our hill, whoosh, then we start going up again. Now in calculus, Cal 1, our focus is this derivative. So when we talk about increasing and decreasing, we want to think about it in terms of what's the slope of the graph there. So what is the graph doing when we're increasing? So if I tacked on a tangent line to those points, what does the slope of the tangent line look like when we're increasing? Greater than 0. Now, yep. So greater than 0 is positive. That's our other word for greater than 0. So everywhere the graph is increasing, the slope of the tangent line is positive. So increasing means slope is, well, let me write the whole thing. Slope of tangent line but the whole expression phrase, slope of the tangent line, is just a code phrase for derivative. And then our decreasing is when the slope is the other way around, negative. So this means if I have a function formula and I can figure out the derivative, I can look at where the derivative is positive. That tells me the graph is going up for those numbers. I look at where the derivative is negative. That tells me where the graph is going down. And then my boundary points on those regions are where the slope of the tangent line, where the derivative is 0. So we can, from the formula, and then from the formula of the derivative, we can actually get a kind of vague picture of the graph. And this is the crap people would do before they had calculators. So some functions are going to be kind of boring in terms of where is it increasing or decreasing. So this function, where is it increasing? So if I sketch in like some tangent lines, even as we get towards the endpoints, they are still ever so slightly upward tilting. So the slope of the tangent line for this whole graph is positive everywhere. So this graph, this is increasing everywhere. When is it decreasing? Never. So if it is increasing everywhere, if the slope of the tangent line is always positive, then the graph of the derivative would actually be always positive, always above the x-axis. But thinking through, here's my graph of my function, what would my graph of my derivative look like? Like, it's a very weird process to think through. So we're going to practice. So earlier we had f of x equals x squared, and we figured out that the derivative was 2x. So we're going to look at what our function is doing, and we're going to compare that to what the derivative is doing. So when I look at my function here, what is my tangent line doing at first? As I start moving from the left edge of the graph, what are these tangent lines? They're decreasing. So when the original function is decreasing, what are those slopes of the tangent line? Are those positive slopes or negative slopes? Negative. And then when we look over here at our graph, the y values are negative. Now, when the original function is neither increasing nor decreasing, then the derivative is 0. So our flat line, our tangent line is flat. Our derivative is 0. And then when our function is increasing, the derivative is positive. So with practice, you can actually be given the graph of the derivative and think about, all right, where is this derivative negative? Where are the function values negative? That's where my original graph is decreasing. Where are the function values positive? That's where my original graph is increasing. Where is it 0? That's where my function has a tipping point, a max or a min. Or a flat line point. Doesn't technically have to be a max or a min. All right, so our next graph here. So this is our graph of the function, and they're wanting us to say something about the derivative. So when I'm looking at my graph, I'm increasing up until it's not easy to estimate these numbers on a shitty graph like this, but it looks like it's in between -2 and -3. So maybe like -2.3. And then we look at the other side. Yeah, it looks like +2.3. So when we're talking about what is the derivative, when we're talking about what is the derivative doing, the first thing we typically solve for is actually where is the derivative 0. So that's why I was like trying to figure out what those x values are, because those x values are the tipping points between where the derivative is changing. So for this graph, it looks like roughly the derivative is 0 at x equals -2.3 and x equals +2.3. Now, when we start talking about where is the derivative positive, like just looking at the graph, I'd say, well, it looks like everywhere before -2.3 and then everywhere after +2.3. Now, when I say words like that, all the numbers before or all the numbers after, that is an interval. So we are going to use interval notation to describe these events. So it can be helpful to actually draw a number line to organize the information. So our tipping point was -2.3, and our other tipping point was +2.3. So again, those are the zeros for the derivative. So everywhere before -2.3, I've got positive slope. I'll sometimes even draw an upward arrow there. The same thing, everything after +2.3, upward slope. So our intervals here, we're going to say from -infinity to -2.3. And I'm going to write the word and 2.3 to infinity. Now, WebWork gets kind of stupid about the and. So in the past, when we wrote interval notation, like in pre-cal when we did domain and in college algebra, we used a U to stick these two things together. And like WebWork should take the U, but for some reason, almost all of our homework questions where you enter an answer like this in Cal 1, they don't want a U, they want a comma. I don't know why. So I wrote the word and here, but when you're doing your homework, don't be surprised if it's a comma, not the union symbol, even though you've got a button for the union symbol. All right, now our negative are decreasing That's where the graph is going down. We're swooping down on the crazy roller coaster. So I'll put little minus signs on my number line, and I'll sometimes put a downward arrow for that whole region. But this is decreasing from negative 2.3 to positive 2.3. And I'm writing the word interval under that to say that is an interval, not an ordered pair.
No.
So when we're talking about where is it increasing or decreasing, at the 0 points, it's neither increasing or decreasing. So we're always going to use parentheses on these. Like we can actually have really weird, like if we have like a piecewise graph that just like chops the graph at a piece, we could have an interval where we'd have like an inclusive bracket, but it's very, very rare. And most of the time we're more concerned with like, what's the region? The boundary points are like a separate part of the problem. All right, so now we just played around and figured out those turning points and everything. We're going to try to interpret that into a graph here. So I'm going to scroll a bit back and forth. So we figured out the derivative is 0 at negative 2.3 and positive 2.3. So we're going to plot those points first. So if I say the derivative is 0, 0 is the y value. It occurs at x equals negative 2.3, so negative 2.3, and positive 2.3. Those are our zeros. Then before negative 2.3, our graph was increasing. What does increasing mean for our derivative? What is the slope of the tangent line when it's increasing? Yep. So we've got positive slope. So positive slope means positive y values for the derivative. So it's going to be above the x-axis. Those are positive y values. And then past positive 2.3, it's also positive values. So now between those 2 points, that's where the graph was negative slope. So I have negative y values. So I have to connect the dots. Now, all of my numbers in there have derivative values. And the graph like smoothly changes between them. So I shouldn't be seeing like weird breaks. This isn't going to be a V. It's going to be a smooth curve between the two. So maybe something like that. Now, I don't know for sure that that's 0, when x equals 0, that my y value is negative 2. Maybe the y value is negative 5. Like maybe that dip should be further down. But I know roughly that the shape of my derivative is going to be a parabola. My graph was increasing, so positive y values. It reached a tipping point, then decreasing, negative y values, and then reached the bottom of a hill and then started going increasing again, so positive y values again.
Wouldn't it be like, with the derivative, there wouldn't it be from wherever x is 0, that's technically increasing on that stuff, though, isn't it? Before you get to your point.
So like that's our 0 point. That's our other 0 point.
Right, I just mean like, technically, if you were looking at that and you were just like, wouldn't it be like where X is 0, Y is -2 or whatever? From then on, that whole thing is.
The derivative is increasing.
So it's just the, we're just thinking the.
So when you say the derivative is increasing, you're looking at the graph of the derivative and you're saying that graph is then increasing. It is. If we took the derivative of the derivative, then it would be a diagonal line.
So this is solely just the.
Yes. So we're not looking at where is the derivative increasing and decreasing. We're looking at where was the original graph increasing and decreasing, which tells us where the derivative graph is positive and negative. That's part of the confusion here. When you're first learning increasing and decreasing, you have to like keep remembering, look at the increasing and decreasing here, look at positives and negatives here.
They're so basic, you know.
Yes. All right, now I think we have some web work questions that do this. So we've got a wacky graph of a function here. This is a, looks like 1 over x plus 1, to be honest. That's probably what it is. But just based on the graph, and then I've got, well, he threw out C, but I've got A, B, and D here from WebWorks. C was probably really stupid. So we want to look at our graph and what it's doing and think about where is the derivative going to be positive and negative. So what is my graph doing originally? Like, is it increasing or decreasing here on the left? Yeah, it's almost flat, right? Like it's really close to flat here on the very left. But as the graph keeps going, we see the values are going down. So we're going to say this whole stretch of the graph is decreasing. But we're going from almost flat to almost vertical. Now, what about the other side of the graph? It's also going down. We're going from an almost vertical line to then an almost flat horizontal line. So both sides of my asymptote here are decreasing. So that means both sides of my asymptote in my derivative should be negative. So when I look at A, because these are all our attempted guesses at what the graph of the derivative is going to look like. I want almost all of my y values to be negative. In A, these are all positive y values. So not A. On B, everything looks negative. And then D is a little weird. But D is tempting because D has the same horizontal asymptote as our original graph. But by looking at that higher horizontal asymptote, technically I've got a whole bunch of positive numbers and then a 0 and then a whole bunch of negative numbers. So D is not the graph of the derivative. There's some positive y values mixed in. So with our choice of 3, B is the only graph where everything is negative, except for where our asymptote occurs. So now notice both sides are heading down towards negative infinity. And this is where it's weird. If a horizontal line has 0 slope, What slope does a vertical line have? Yep. And a vertical line is all rise with no run. So rise over run, that'd be some number over 0, undefined slope. We can also, though, when we were doing our limits, when we got a fixed number over 0, that was infinity for our limits. So we sometimes say vertical lines have infinite slope. And when we look at the derivatives, that's what we see when it's approaching negative infinity as we're getting closer and closer to that asymptote. That's why we see the graph like getting super extreme, almost vertical. Our derivative should also get almost vertical. It'll either point towards negative infinity or positive infinity. All right, so we have a little theorem. If f is a function and a is in its domain, if f is differentiable at a, then f is continuous at a. So to claim that something is differentiable, you are claiming that the particular limit at that point as h goes to 0 exists. And in claiming that limit exists, you actually get everything you need for continuity inside that definition. It's a pain to prove, but it can be proven. So this theorem is just saying like, hey, if we know something is differentiable, that automatically tells us it's continuous. The reverse is not true. I can have a continuous function that is not differentiable at a point. And we're going to take a look at that. So if we look at the function, the absolute value of x. So the derivative does exist for almost this entire graph. And the derivative is actually very silly because it is a very simple derivative. So when I look at this graph, and I'm looking at the slope of the tangent line, well, this graph is really just two lines coming together at a point. So when I look on the left side, what's my slope of the tangent line? It's all negative. And in this case, it's a particular number, the absolute value of x. This is a slope of -1. Everything on that side of 0, the slope of the tangent line is that line on the graph. The slope everywhere there is -1. And then on the reverse side, anywhere I pick a point and say, what's the slope of the tangent line? That's just the slope of that line. The slope on this side is +1. So if I'm going to graph the derivative, before x equals 0, my slope is -1. After x equals 0, my slope is +1. But the question is, what's the slope at 0? So we're going to look at these two individual limits. So we're looking at our limit, our derivative at 0, but we're looking from each side. All right, so f of 0 plus h from the left so this is where we want to remember what the piecewise definition of absolute value is. So it's negative thing if x is less than 0, and it's positive thing if x is greater than or equal to 0. So when we're looking at the left side of 0, that's when x is less than 0, our function formula is negative x. So I'm going to do the negative of 0 plus h minus then my function formula. So let me use some extra parentheses. Then my minus my function formula is the negative of 0. All divided by h. So we actually end up with that negative sign in front of the 0 plus h. That's going to be distributed into the h. Forgot my limit. So we have negative h over h. And that just cancels and becomes negative 1. So my slope on the left side is negative 1. But if I do that same process for the right side, the limit as h approaches 0 from the right, now our function is just x. So we're just going to get 0 plus h minus just 0 all over h. So the limit as h goes to 0 of h over h. H divided by h is now 1. So our derivative from either side does not equal. So when I go back to my graph of my derivative, I actually have open circles on either side there. So whenever the function comes to a corner point instead of a smooth transition, at the corner point, we say the derivative does not exist. Now, most functions don't have corner points. The absolute value is like the weird singular example. There's a few really weird other ones that show up on occasion, but most graphs actually smoothly transition everywhere because they're functions. They do good, nice things. All right. I will record a video to finish covering the rest of these examples. But let me stop this.